Welcome to our talk. My name is William, and this is my teammate Kent. We both work for the analytics team at Unity Technologies. Today's talk, we'll talk about our journey moving from a, wow. Okay, hope that works. Our talk today is about our journey moving from an old data pipeline that uses MapReduce and Hive to a new data pipeline that uses Spark. We'll also talk about some key factors that made this transition successful. We'll talk about how we use Spark in our data pipeline. First, I would like to introduce what we do here at Unity. Unity is the leading game development platform. We offer the 3D gaming engine, tools, and services. Our team owns the analytics product that offer analytics to game developers. And of course, we're hiring. Over 34% of the top 1,000 games are made with Unity. As of Q1 2016, over 220,000 games are made with Unity. There are over 4.2 billion downloads of these games on 1.7 billion unique devices. To give some context about our service, here's a screenshot of our dashboard. Events are sent to our service from games made with Unity. The events are aggregated and converted into key gaming metrics that is then consumed by game developers. Our journey starting point is our legacy data pipeline. Our legacy data pipeline evolved over time to a point that is causing us critical issues. Some of these problems are scaling and performance issues, operational challenges, and overly complex system as a whole. Our decision was to rewrite our data pipeline, and this includes using Spark. The main reason why we chose Spark are we wanted to invest in the next generation technology stack. We believe Spark has a solid ecosystem. This includes the community, libraries, and tools. We saw many case studies that showcase the scalability and performance of Spark. And we wanted a single technology stack that can support both Bash and streaming applications. This is what our architecture looks like with the legacy pipeline. Events are sent from gaming devices to our front end. Our front end bashes the events into files stored on S3. The data pipeline then consumes these S3 files, aggregate the events, compute the metrics, and upload them to MySQL database. Our dashboard then uses the database to serve metrics out to game developers. The middle box here represents our data pipeline. The legacy pipeline uses technologies like Amazon Elastic MapReduce, Hive, and some in-house software. And this is the architecture with the new data pipeline. What changed is the middle box here that represents our data pipeline. Some of the key technologies that we use today is Caldera, Spark, Airflow, and Parquet. A bit about how we develop on Spark. We chose to use the latest stable distribution of Caldera at the time. And that was version 5.7. And that in turn was tied in with using Spark version 1.6. We worked directly on RDDs using Scala and Java. We did this for control, ease of testing, and the ability to use strongly typed case classes. So why not use dataset or Spark SQL? We are interested, but we're waiting for Spark 2.0 to stabilize. One of the key factors we believe helped our transition to Spark successful was our ability to make fast iterations. Fast iterations allow us to make quick changes and get fast feedback. We were able to experiment much more. This helped us catch bugs and issues early in our development cycle. In order to make fast iterations, we have to invest upfront and early. We invest heavily into unit testing. We were able to run end-to-end data pipeline in our development environment. We invested in setting up a solid staging environment, and that includes having a realistic cluster size, using realistic workload, using production data early, and the ability to run repeatable testing. This is the logical flow of our data pipeline. Our data pipeline can be divided into 5 main stages: import, ETL, analysis, export, and backup. The import stage is responsible for capturing snapshot of the external data that we need for processing. The ETL stage validates, formats, and does simple transformation for easy consumption downstream. The analysis stage is the core of our application logic. It does the complex application and computes the metrics. The export stage takes the results from the analysis stage and pushes it onto an external system for consumption by external services. The last stage is the backup stage. It takes our data set and uploads it onto S3 for fault tolerance. An interesting point that I would like to make is that we use Spark as the computation platform across all our stages. At first, we only intended to use Spark for a few stages, especially the analysis stage. But we naturally gravitated into using Spark across all our stages, and this was because of the ecosystem and libraries. It was easy for us to achieve what we want at the scale that we want. One key design principle of our data pipeline is idempotency. Idempotency is important for fault tolerance. We wanted to be able to rerun any batch and get the same results. We wanted to be able to continue running any batch at any stage and get the same results. To achieve idempotency, we made all our input and output immutable, and we use Parquet as the medium for this. Spark also has great support for Parquet files. At this point, I would like to pass the presentation on to Kent, who will talk about each individual stage in a bit more detail.
Thanks, Will. Let's start with the first stage of our pipeline, the import stage. The import stage, we take a snapshot of the data needed for the pipeline to run. It takes snapshot from metadata tables stored in MySQL and raw event files stored in S3. This ensures idempotence on retries. We read from MySQL using the Spark JDBC API. We notice that on large data sets, we definitely need to parallelize the reads. So we use the partition column feature that partitions your reads into different partitions, therefore parallelizing and speeding up your reads. When using the partition column, make sure you do the filtering on your data frame side and not on MySQL side, because if you combine the two, it can generate slow queries. The next stage of our pipeline is the ETL stage. The ETL stage takes care of sanitizing, transforming, and grouping of data. Let's go back to ETL. Okay. Sanitizing, transforming, and grouping of data. Sanitizing as in cleaning up malformed data, transforming as in transforming timestamp formats to another format, and grouping because we receive a batch of mixed raw event types, so we want to bucket it into its own event types. This ensures consistency and quality of data for the downstream stages. We also convert our input JSON to case classes to ensure type safety. And also we use the RDD API to do all our transformations. And when we save to Parquet, we actually convert our case classes to data frames and use the Spark SQL API. A few tips is to avoid nulls. We use Scala, but since our legacy pipeline is Java, there was some code that still have nulls, and it actually gave us headaches downstream. So avoid nulls. Another tip is to repartition your output RDDs to remove the skews. Since our input files come from S3 and it's dictated by our API server, and and it can vary in size, we do a repartition so that it will all be even size. The next stage of our pipeline is the analysis stage. Most of the business logic is in analysis stage. We compute user level and aggregate metrics that is then consumed by front-end or other internal services. We implemented the analysis stage using a single Spark job. We do this so that we can heavily use caching of RDDs. But it also has a few disadvantages. One is having very complex DAGs. And when you have a complex DAG and you have a failure, it will depend on where the failure is. And sometimes it takes long because it has to recompute a long chain of operations. Also, we noticed that since we cache a lot of RDDs, it sometimes spills to disk. And when it spills to disk, we notice some failures. Due to the nature of our data, skews are unavoidable and affects our scaling. So to handle skews, we prefer the union reduced by key pattern, which is essentially having your two input RDDs that you want to join. You actually convert them to the same format and then union them and do a reduce by key. We do this so that this solution is more robust because it does a local reduce on each worker. We prefer this method over the join and aggregate pattern. Also for handling skews, when one of your table is small and can fit in memory, you can do a map join. But the problem is when both of your tables that you want to join are big and cannot fit in memory, we use the Skew join. Skew join is a library shared by Sara. It's essentially a block join with replication. What this means is it does a count sketch to get your key distribution and then replicates each key based on that distribution. On this stage, we also do a lot of shuffles. And we all know that shuffles are expensive. So we use partition-aware operations. And also, when we want to do a repartition, we don't really call repartition explicitly. We piggyback over prior shuffle operations. An example of this is, let's say you want to do a reduce by key. You can pass in as a second parameter a hash partitioner or any other partitioner with the number of partitions. Spark is sensitive to partition memory size. It is directly related to your executor memory setting. And fewer large partitions can cause out-of-memory errors, and too many small partitions have a high shuffle overhead cost. So you want somewhere in between. On our end, we compute the number of partitions dynamically by collecting and using the dataset statistics. So we actually read the generated output from HDFS, read the file size, and compute our estimated number of partitions. What this means is, as our data grows, the number of partitions scale as well. Partitioner matters a lot. The resulting number of partitions on joins depends on input RDDs. Join mostly use the default partitioner logic, which basically takes the partitioner with the largest number. And if there's no partitioner, takes the largest RDD partitioner number. RDD has partitions, but not necessarily a partitioner. You have to be careful on this note. And also, when reading from Parquet, it doesn't give you automatically a partitioner. And also, some operations remove the partitioner, like map or keyby. I want to talk about a few differences between Hive and Spark. Spark RDD operations are sensitive to partition size and can often hit out-of-memory errors with the wrong configuration. But with Hive and MapReduce, it's more forgiving. Also, in terms of Skew handling joins, Spark has a broadcast join, which is essentially a map join. But Hive has other Skew handling joins built in, like bucket map join. The next stage of a pipeline is the export stage. This stage exports the computed metrics in the analysis stage to an external storage like MySQL. This makes it easy to consume analytics data from our front end. We write data to MySQL using the load in file command with CSV. We batch to larger CSV files using Coalesce and Spark CSV. This, using the load in file, I think is one of the fastest way to load data to MySQL. Also, we sort by primary key. This lessens the disk seeks when writing to MySQL and further speeds it up. And the way this works is by first having a list of CSV files, we parallelize them to create an RDD. Then for each partition, we do a load to MySQL. The last stage of our pipeline is the backup stage. On this stage, we back up the process data to S3. We open source that logic with this project, Parquet S3 Backup, which I will show you the link later on. We use HDFS for collocated working data set and use S3 for long-term backup. When saving to S3, we first coalesce Parquet files locally before saving, as S3 also has a small files problem, same as HDFS. So you want the ideal size. We also use the S3A protocol, which is the newer protocol that can handle up to 5 terabyte file sizes, and it's also faster than the older ones. Also, when saving to S3, we use the direct Parquet output committer, which skips writing to temp folders. The default behavior actually does, after writing to a temp folder, it calls a rename, which is essentially in S3 a copy and delete. And we notice it's very, very slow. This direct Parquet output committer was deprecated in Spark 2.0, so you have to use the other one I listed here. We use Airflow as our pipeline for scheduling and defining our DAGs. Airflow has a backfill feature and was easy to set up and simple to use, and fits our short to midterm needs. It also supports different kinds of operators like Bash, Python, and MySQL, and it was very extensible. You can easily write a Redis connector or operator if you want. On our end, to submit a Spark job, we use the Bash operator that calls Spark submit. So we have the legacy system and the new system. The legacy was all in Hive tables, so we needed to do a Hive data migration. So we have a one-off Hive data migration Spark job that reads from our legacy Hive tables in S3 using org format. It was very easy to load it in Spark. You just call the Hive API, point it to your S3 folder, which on our end, the Hive tables are actually stored in S3. And then after loading, we do the same thing as what we do on the newer pipeline, which is validate, sanitize, transform, like the ETL. And this also ensures this having the same format for both on the migrated data. So here are the results of our new architecture. Take note, this highlights our success with migrating to the new architecture using Spark, but it's not representative of Hive versus Spark because we made a lot of optimizations along the way. But most of the business logic is still kind of the same. And both systems have the same total EC2 instances cost, but uses different instance types. So on the old system, the one run of our pipeline takes 12 hours. and the new one takes 2.5 hours. And we experimented with having twice the number of workers. We got 1.5 hours. So it kind of proves to us that our solution, our new architecture scales. Here are the links for the Skew join that we used, and also the Parquet S3 backup that we open sourced, as well as the MySQL uploader. Thank you so much.
Okay. Any questions for Will? And oh, lots. Okay, so if we start from this side, and I'll work back. There we go.
Hi. So you said you figure out the number of partitions you want, given you infer it from the data. So what are your heuristics about this? Like, do you consider the number of records, the size of the data, and how big are the partitions going to be, or what are your heuristics for this?
Will answer that
one? So can I interpret that question as why we actually do control the partition size dynamically?
Not exactly. No, I can understand why you do it. I want to understand how you do it.
How we do it?
Like, given the data, how do we infer the number of partitions that you want?
Okay, so our data pipeline is pretty much taking in new batch data and taking in our existing data sets that we already have, and then kind of compute them together, right? That's a standard data pipeline. So we kind of know already from past computation how big our data set will be. And because our batch is not like 1 day or 1 week, it doesn't change that much over time between previous and current. So we can use the previous data set to estimate how much data that we expect, and then grow the partition based on that. But there's always a small lag because the batch data may increase the data set size.
So yeah, I mean, I can understand that you can record the size of the previous data sets, previous version of the data sets, but how to decide how to translate it as a number of partitions?
Oh, that number, that magic number, right?
Yeah.
That is trial and error. I mean, it depends on your executor size, how much memory you have, and also about your joints. How big is your joints? For us, we have some stages that has a lot of joints that joins a lot of data together, and that one requires us to use a lot smaller partition size. But in other transforms that use more simple joints, we can afford to have larger partition size. So it's trial and error.
Yeah, okay, so I guess my last question can be, do you have any idea how big are your partitions in terms of megabytes, for example?
Megabytes?
Yeah, for example. So like, do you have any idea how big are your partitions? And because I had assumed that this was the kind of heuristic you could use.
Are you talking about our partition size, how big they are?
Yeah.
Or the executor?
Because that's one thing that
because
matters.
It's relative.
Because it's gonna influence the amount of memory problems you're gonna run into.
So maybe I'll just give you some numbers. Right now we are looking at an executor that has around 3 threads, that means 3 cores, that has around 10 megabytes of memory, 10 gigabytes of memory, and each partition size against is about only a few hundred megabytes. Because we are using RDDs, and once the strings get into Java objects, it kind of expands quite a lot.
Okay, cool. Thanks.
And take note that when the partition size that we estimate is from Parquet files. So let's say a 100 megabyte Parquet file per partition will translate to like a gigabyte or something of memory once all the Java translation and uncompressing occurs.
Okay, cool. Thanks.
Any other questions? I think I saw a few other hands. Oh, over there. Thank you.
I would like to know if you have tested to run your job, your Hive pipeline on Spark, because you can use Hive and MapReduce, and now from a couple of months, I think, on Spark also. And what was the performance?
Is the question, are we invested to use Spark instead of
No,
continuing-
Hive and Spark.
Oh, Hive and Spark. Oh, okay. So when we previously have our Hive pipeline, it has a lot of very, very complicated SQL, sometimes like 7 levels deep, and it's super unmaintainable. So that was actually the main reason, one of the main reasons why we want to switch to the RDD flow. And the next step, I guess, for us is we want to use the data sets because we want to utilize the Tungsten engine.
I got a question as well. Why did you choose? Why did you decide to use MySQL as the destination database?
Legacy purposes. We're planning to switch to HBase, actually.
All right.
Some of our pipeline is already HBase,
Okay.
so that's the next step.
Good choice.
Any other questions? Oh, right at the back there. Thank you.
Wanted to ask, are your Spark processes like lifelong lived jobs? I mean, are they continuously working, or are they being executed just once, like an ETL?
We have continuous events coming in, so we are continuously running. Right now, we are looking at maybe a 2-hour batch cycle, but it is not a streaming application right now. It's batch-based.
Okay, thanks.
Okay, one more question? Anyone? Right at the front, okay. Just that one. And I've been asked to remind all of you still here that there is an attendee reception as well in the expo area, okay? So immediately after this last session finishes, if you want to head down there, there'll be a reception for you.
Yep.